So let me start with an interesting video here. As you can see, there is something very spectacular about this particular video. What you're seeing here is some colloids getting trapped thanks to an optical beam. This configuration is generally called as an optical tweezer. So this forms a beautiful kind of a pattern, and the particles here are kind of polystyrene colloids, roughly about a micron, and they are assembling themselves in an optical beam. What you're seeing here essentially is an optical tweezer, and into the tweezer the particles are getting assembled. So what is the background behind this particular thing? What is the brief history behind this? Let us check this out. So roughly around 1960s or so, there was a lot of interest and also an emergence of an important invention, which is the laser beams. The laser beams actually were created thanks to some very interesting emergence in terms of understanding of light matter interaction. This created very interesting light sources which were extremely powerful. The question was, can these powerful light sources be of any use at all? That was the question. In fact, the postulate was that lasers were solution in search of a problem. This was a very interesting notion because everybody knew that there is something very interesting about lasers, but can one use it for a specific kind of a purpose was the question. The understanding of radiation pressure and electromagnetic momentum was kind of very well known during that particular time. So with this new light, the question was, what can be achieved? Can we really understand something more than what is already there? Can these light sources be used for certain applications? One of the very interesting aspects was to look at atomic manipulation, where you can trap and manipulate atoms. And in the other extreme was to see whether you can manipulate life itself, which is something very fascinating. The other aspect is to use the light in biology as a way to image processes. This was something which is very fascinating, and there was a lot of interest during that particular time. So the questions which people had to address were multifold. And one of the important questions that had to be addressed during that particular time was, can lasers be utilized for some kind of a manipulation? The second question was, what is the nature of the forces due to this kind of light matter interaction? And what kind of degrees of freedom can you really excite using such kind of light matter interaction? These were some of the very interesting questions during 1970s or 80s. And one of the pioneers in this particular area was Arthur Ashkin, who devised some very ingenious experiments in order to address these questions. Starting in 1970s, he showed that you can accelerate objects using light sources. So you essentially have a light source and you have an object that gets accelerated further. And you can also trap an object. Okay, and this trapping actually was thanks to the two different light sources. For example, you had a light source coming here and a light source coming here, and you could trap an object in the counter-propagating direction. And in 1980s, there was another important invention which was called as an optical tweezer, which eventually led to the Nobel Prize for Arthur Ashkin, by the way. Now, acceleration, trapping, tweezing, these are all extremely important ways in which you can understand light matter interaction. And to go further, one needs to understand the nature of forces per se. So Ashkin, in a very early time, recognized that there is quite a lot of interesting forces associated with the interaction. The first and the most important association is something called as the gradient forces. This gradient force essentially arises because there is a gradient of intensity of the laser beam. So if you have a laser beam, generally speaking, the laser beams are Gaussian in nature. So these laser beams have a gradient force. And what happens is, once you have such kind of laser beams, the particle comes in. Because of the fact that the laser beam is Gaussian in nature, the particle gets kind of confined to the region of interest, which is exactly at the center. The other force is called as a scattering force. The scattering force essentially is the light which is emanating from the laser beam, and that actually pushes the object in the forward direction, and this propels that particular object. So as you can see, gradient forces bring the object towards light, scattering forces push the object away from the light. So these two forces actually participate and also kind of counterintuitively help one to achieve either propulsion or trapping. If the gradient force is dominant over the scattering force, you can now trap objects. If the scattering force is dominant over the gradient force, then you can propel the objects. So these two forces were identified in a very, very, very early time. In recent times, there is also an interesting force associated with spin curl forces, which is relatively new, and it has turned out to be very fascinating, because now you can create some very interesting degrees of freedom where you can rotate the object and also revolve the object. So you can rotate it over axis or revolve it with respect to an orbit which you create. So these spin curl forces have very interesting physics and associated mathematics. Hopefully at some point of time I'm going to talk a little bit more with respect to the kind of forces. The interesting aspect, as I mentioned, now you can achieve translational degree of freedom. You can confine objects thanks to the tweezer, just like what we see in this particular video, where you essentially have the objects being confined thanks to the gradient forces which are greater than the scattering forces. You can also create rotational states and also revolution with respect to an object. So these are some of the fascinating aspects of optical tweezers. There are so many interesting things. This is not just a curiosity, it has turned out to be extremely important, right from atomic physics all the way to molecular biology. And even in certain cases, it has been also applied to some space missions in the context of propelling objects due to the radiation pressure. And that is another topic hopefully I'm going to cover at some point of time. So coming back to the proposition of lasers as a solution searching for a problem, we now know indeed that laser beams are solutions to many, many problems.